this is work that has mainly been done by Georg and Stefan, who are also here today. Well, they came to visit us from Austria, and they were looking for a project. So Erik and I ended up giving them a couple of boxes of Lego. And then after a while, they came back with a very nice robot. So the goal of the project was to use automated learning techniques to reverse engineer the identifier 2. So that's the device that you see below here. So it's a handheld reader that you can use in online banking. So you insert your banking card in it, you enter your PIN code, and you confirm a transaction. So what we wanted to have from this device was to learn its state machine, the internal state machine. And this is something we previously did for bank cards. So for EMV bank cards, to be specific. So that's with a chip on it, so there's not much to learn from the magnetic stripe cards. But to the chips, you can actually send commands, and then you get output back. And there we were able to extract some interesting models. And some other work we did previously was to actually look at the identifier to see, well, the goal was to see if we could use it for interesting purposes, but it turned out that it's not something you want to use for interesting purposes. So it's a device that was originally developed by Todos, which is now part of Gemalto. It uses the EMV cap standard to sign data. EMV cap is a proprietary extension, basically, of the EMV protocol, which is public. But, well, by now it's been largely reverse engineered, so we know, for most of it, we know how it works. This specific device can be used either with or without USB connection. So if you connect it via USB to your PC and you want to transfer some money, you get a somewhat meaningful message on your device after you entered your PIN code, and then you confirm this to indicate that you agree with this transaction. So this is what Gemalto called see what you sign, and according to their website, it was the most secure sign what you see end user device ever seen. So then I hope we will never see the other ones. But, well, in general, it's a good idea, because before we all, or in Europe at least, we have these devices. You enter some random number and then your PIN code, and you confirm a transaction. So you don't really know what you're confirming. But at least with this device, it was possible to have more meaningful messages. So this is more or less how EMV cap works. So you enter your PIN code on the device. This is sent to your bank card. This bank card says to the device, OK, this PIN code was correct. Then you enter the challenge that you get from your bank to confirm your transaction. This challenge is then sent to the card with a specific, well, generate AC command. The card then in turn computes a MAC over this data and some of its own random data. And then based on this, response is generated, which is entered at the bank side to confirm your transaction. So this is how the identifier works. So you have a bit more data because it's connected via USB. So again, first you have to enter your PIN code, confirm the PIN code, and then some data is sent to the device. So this is some random data and some text, which will be displayed. So you have something like this, which contains a message containing the amount that you are going to transfer. Then the user has to press OK to confirm this. Then the device sends back to the PC, OK, the user just pressed OK. And the PC says, well, great, now please generate a response for me. And then, just like with regular EMV cap, the response is generated. But already here you see something which is a bit weird, because apparently the device first needs to tell the PC that the user pressed OK. So instead of getting the response as soon as the user pressed OK, it first informs the PC that the user pressed OK. So, well, we were wondering what would happen if you just forget about the user and ask to generate the cryptogram immediately. And we found out that this actually worked. So it was a very user-friendly device. You didn't even have to press OK anymore. So we had contact with the bank, and then they came up with a new device and had to stop production, but there are still loads of these old devices hanging around. But luckily, I think almost nobody uses the USB connection anyway. So they still enter their random numbers, so it's, I guess just as secure because you still don't know what you're confirming. So this was manual analysis that we did before, and now we wanted to see if it was possible to do this in a more automated way. So for this, we used a tool called LearnLib, which is an implementation of an adapted version of the L-star algorithm, which is some well-known algorithm for learning finite state machines. So the output is a complete Mealy machine. So if we have a state, we have a set of inputs that we can send to the device. So in this case, there are USB commands and button presses. And then the device will return some outputs or not. And then the way this algorithm works, we have two components. So we have a learner and a teacher. The teacher, is assumed to know what the final state machine is that you are looking for, and the learner obviously tries to learn it. And he has three actions that he can do. He can send output queries to the teacher. So using these, he can ask to send, for example, a USB command to the device, and then the teacher will return to him what the output of the device was. He can reset the device to its initial state, and using these two actions, the learner will try to come up with a hypothesis, and then I can ask the teacher if this hypothesis is correct. Unfortunately, our teacher does not have full access to the device, so we have to approximate these equivalence queries. So there are two methods that we can use for this. We either use random traces. So if the learner sends a hypothesis, the teacher just tries loads of random traces against the device and see if this matches with the model that he just got. And if all the traces match, so you set the maximum number of traces, then the model is considered to be correct. Or we can use a W method. This is more expensive time-wise. But if you know an upper limit for the number of states that you are looking for, this can guarantee a correct solution. So we can use this technique to reverse engineer, like we did here. Then you can have a model which you can inspect for correctness and security. You could use it as a basis for more targeted fuzz testing, or you can use it as a basis for formal analysis, for example, as input for a model checker. So, the bank came up with a second device, so we had two different versions that we could analyze. So usually every response is different because there's a counter included there. So for this we used, so instead of a real EMV card, we used a programmable smart card because we wanted to fix the output, because otherwise the machines would become infinite. And also otherwise entering pin codes would get a bit more difficult. And as I said before, we did this with EMV smart cards, so then we could do it with just software. We just needed a smart card reader, basically. But now we needed physical interaction because we needed to be able to press OK buttons and enter pin codes. So that's where the Lego comes in. So we had loads of boxes of Lego, and then Georg and Stefan had some days to play with it. So it consists of, or it uses 3 motors to actually press buttons. So obviously we have to press the OK and the cancel button, and we pressed 1 digit. Since it's our own smart card that we programmed ourselves, we just let it accept any pin code. So that's well, quite convenient. So 1 digit was good enough in this case. Also, from the Raspberry Pi, we controlled the power on the USB line. So to reset the device, we actually cut off the power. And the USB commands that were sent via the Raspberry Pi to the device and then returned to our LearnLib tool. So this is the latest version of our Lego robot. So before it was, so now it's pressing the 5, but before it was pressing the 6. But we got some problems with some non-deterministic behavior. And after some debugging, which is quite annoying if it only happens after a couple of 100 runs, I found out that actually the button got stuck. So apparently it's not built to be pressed thousands and thousands of times. But luckily we had about 10 digits, so I moved the motor and now it's pressing the 5 again. So it will work for a couple of more thousand more times. So this is from the other side. You can see the Raspberry Pi there with the extension board controlling the motors. And this is then a simple model, or simple models that we found out where we use very coarse-grained actions. So we combined several USB commands or button presses. So the top one is the old version, and the bottom one is the new version. And you can already clearly see that there is a difference. And if you would follow the path from the start state, you could see that it's possible to get to this red transition, which generates a valid cryptogram without having to press the OK button. Now, if we use more fine-grained actions, then this is the model that we learned for the new device. And this already becomes a bit more complicated to analyze by hand, but is still somewhat doable. And I will not even show the one from the old device because it looks really terrible. It's about twice as big with very weird error states, and I'm not sure what they try to do there. But if we have these complicated models, then we can use these as input for model checking. So we converted the models that we got, so that you saw before, to LTS files that could be used by the model checker CADP. And then we can use model logic to check for certain properties in a model. So in this case, we verified whether you actually had to press the OK button before you would be able to generate a valid cryptogram. And then the tool actually could give us a valid attack trace for the old device and tell us that it was not longer possible in the new version. So to conclude, these automated learning techniques can be very useful in security analysis for embedded devices. They can be used in combination with model checkers to automatically find security vulnerabilities. And I guess one of the best reasons is it's a very good excuse to play Lego during your PhD. And I think there's none of my colleagues who walked past my office without noticing that I had loads of boxes of Lego around me at some point and just had to come in to play. Now, I'd like to thank you for your attention, and I can quickly show a video of the robot in action, if I get it to work. I can see it. Oh, come on. Mm-hmm. Doesn't want to cross the border. So this is the first version of the robot. No, Lego works surprisingly well. It's better designed than the device.
Actually, the device broke 30 of them, the Legos, right?
Yes.
So,
Lego is still working.